Good morning. My name is George Tynan. I'm a professor in the Department of Mechanical and Aerospace Engineering here at UC San Diego, and also a member of the Center for Energy Research. And today I'm going to talk about what is the future for nuclear-based energy sources to meet global energy demand. Nuclear fission, which is the first topic that we're going to discuss today, is a process by which a fissile nucleus like uranium-235 is bombarded with a neutron, and the fissile nucleus then splits in two and releases energy, and also releases a couple of extra neutrons, which then diffuse through the background of the reactor, and then one or more of those daughter neutrons strike another fissile nucleus and repeat the process. And if we can engineer the core of this reactor such that we have a net steady state, that is, for every incoming neutron that's absorbed, we have one additional neutron that's absorbed in the next generation of fission, and the other excess neutrons are lost either by diffusion or absorption in the reactor, then we can have a steady state power production. And that's the basis on which the so-called fission chain reaction proceeds in a conventional nuclear reactor. Reactor designs have gone through an evolution from the very first designs in the late 50s, early 1960s, through the bulk of reactors that you'll find around the world today called second-generation reactors. And today, around the world, a variety of countries are beginning to build third-generation reactors. And I'll talk a bit more about the distinctions between those in a few minutes. Most current reactor concepts are based on what's called the light water reactor, LWR concept. We have the reactor core is this region down here. It's immersed in high pressure water. That's this green region. That water gets hot by the release of heat from the nuclear reactions, and then the water in the primary loop circulates around through this dark green channel as shown here, and exchanges heat with a secondary loop of water, which boils into steam, and the steam runs the turbine. Most of the fuels use uranium mixed oxide fuels. Water is the moderator, that is what sort of controls the rate of the reactions. It's also the coolant. Most reactors use a once-through fuel cycle, that is, after the fuel is exhausted, it's removed and considered as waste. A few countries around the world have closed the fuel cycle. I'll say more about that in a few moments. These reactor designs have very high power densities, and as a result, they require very high safety redundant systems in order to minimize the chances of a loss of coolant in the core. A loss of cooling in this core region can cause serious failure of the reactor core if that happens. As I said a few moments ago, more recent reactor designs have moved to what's called Gen 3 or Gen 3 Plus concepts, which incorporate a variety of passive safety systems to try to reduce the probability of a severe accident. Schematic of a design that's been approved for construction in the US called the AP1000, where the reactor core is here. And then there are a variety of mechanisms that will naturally remove the heat from the reactor in the event of a loss of coolant incident due to some external event, like a power failure or so forth. The natural occurring processes of natural recirculation are sufficient to remove the waste heat from the reactor core and keep the core temperature below the maximum allowable temperature. And it is thought that this sort of a design approach of passive safety leads to a less complex system, and a less complex system will therefore have a higher reliability and a smaller likelihood of any severe accidents. Key issues for nuclear energy are economics. This slide is taken from the U.S. Energy Information Agency and estimates what's called the levelized cost of electricity from a variety of energy sources. And if you look at the table, you'll see this with the rectangle, it estimates the capital cost as well as the cost of electricity from nuclear systems. And you'll see that they're in the ballpark of fossil fuel energy sources, but you'll also notice that there are some fossil fuel energy sources, particularly natural gas sources in this country, that are significantly cheaper. And then for comparison, there are also estimated costs for a variety of renewable energy sources. Another issue is the capital cost for construction of a power plant. This plot shows the actual capital costs for construction for power plants in the US in red, and the dark blue data points are for the experience in France. And the horizontal axis is the total amount of power installed up until that point. And so you can see that as more and more power plants were constructed in the US and France, eventually the costs actually began to increase, not decrease. And so this is sort of an inverse learning curve. And this is counter to what you usually expect for most new technologies. Another key issue is the handling of spent fuel. In the US, we essentially consider the spent fuel as waste after it's used for about 2 years or so in the reactor. And so after the fuel is removed from the reactor core, it's usually stored in what's called dry casks, and that storage occurs on site around the United States. Other countries have chosen to close the fuel cycle sort of by the processes shown here, particularly the French. The Scandinavian countries and Japan have chosen to do that, and that reduces the amount of spent fuel that has to be stored, but it introduces other concerns. The final issue that affects the acceptability of nuclear energy in this country and many others is the concern about risk and safety for nuclear energy. And that's certainly understandable in wake of incidents like Fukushima. But what I've shown here is calculations, real data from operational experience of years of life lost per unit of energy produced by a whole variety of energy sources, from wind energy to the fossil fuels. This is taken by an analysis by a group in Germany, shown in the slide. And you'll see that nuclear is actually one of the safer energy sources as measured by the years of life lost per unit energy produced, terawatt hour of energy produced. Most of the energy demand in growth in the next few decades is expected to be in the developing world, not in the OECD. In the more developed world, Europe, the United States, developed Asia, Japan, and so forth, energy demand growth is expected to be very modest over the next several decades. But in the balance of the world, particularly places like India, China, and so forth, energy demand is growing quite rapidly. And on the right-hand side, I sort of show a breakout of how the net electricity production around the world will grow, and also we show the different energy sources that are used to produce that electricity. And you see that the yellow band, which is the anticipated nuclear energy balance in this mix, is substantial and is expected to be growing along with renewables and hydropower and, of course, the fossil fuels. The challenge, of course, is then meeting the human energy demand and living within the Earth's climate budget. This is a plot of the tons of carbon emitted into the atmosphere as a function of time into the future. And the yellow, sort of orange-yellow curve is essentially the current trajectory that we are on. And the various colored lines show the allowable carbon emission trajectory if we are to meet various levels of CO2 concentration in the atmospheres. The dark blue, for example, would be the carbon emission trajectory for 750 parts per million of CO2, roughly triple the pre-industrial levels. Most scientists think that that will actually lead to very significant climate changes. And so therefore we would probably need to limit ourselves to some of these smaller values. And the key point to note here is that first the carbon emissions must peak, and then they must decrease and essentially vanish over the next century or so. So you might ask, well, renewable energy is growing rapidly, so can't that meet our future energy demands? This plot shows both the light green and light purple curves down here at the bottom actually show the total global capacity of non-hydroelectric renewable power over the last few years. And this is actually the growth rate. And so you can see the growth rates are enormous, 15, 20, 25% per year for renewable energy. And so you might argue, well, can't we simply meet our future energy demand needs by continuing this process? A number of analyses have looked exactly at that question. I would encourage the students to look at this report, which you can find on the web, which looks at California's energy future from now till 2050. And they make a variety of reasonable assumptions about the growth of the population, the economy, the adoption of renewables, and so forth. And the bottom line is the finding in this analysis that we cannot meet these emission requirements getting back to 20% of 1990 carbon emission levels by the mid-century without adopting also some fraction of nuclear energy in our energy balance. Another report was that looked at the national and actually international level by a consortium of National Academy panels from around the world called Lighting the Way, comes to somewhat similar conclusion that it's very difficult to reach these carbon emission requirements without nuclear being a part of the mix. It's not going to be the sole answer, but it also needs to be in the mix. The growth of nuclear energy is expected to be in Asia and India, particularly China and India, and other non-OECD regions around the world. In particular, we expect over the next several decades 200 to 300 gigawatts of new nuclear power plants to be built in the next 2 to 3 decades. One plant is about 1 gigawatt, so this is roughly several hundred large-scale reactors. It's anticipated to remain 15 to 20% of global electricity demand over the next few decades. And my argument would be, if you don't like nuclear energy, then you should prepare to replace it with gas or coal, because that is the most direct replacement for nuclear energy with today's technologies. And that has an implication for the carbon balance for the world. So in closing, is there a future for nuclear energy in the wake of Fukushima? I would argue that the answer is yes. Despite the concerns, it is an available, reliable, and ready technology that can scale to meet the global need. There are also several possible improvements in nuclear-based energy systems. I talked about third-generation reactor designs. There are research projects on around the world trying to look at what would come afterwards, so-called fourth-generation fission. And this would essentially design a reactor that takes the passive safety concept to the ultimate extreme, so that the reactor is physically impossible for it to have a catastrophic meltdown like a light water reactor. And then there's also fusion energy, which UCSD has a very large research effort going on, which again has no possibility of a core meltdown, and you can actually design reactor concepts so that a worst case accident does not require off-site evacuation. That is, the radioactivity release would be small. You can eliminate long-lived nuclear waste, and the reactor components themselves would have an activation time of a few decades to a few centuries, as opposed to millennia to tens of thousands of years. And finally, the fuel is readily available. And so these fusion reactor concepts have been looked at by colleagues here at UCSD. I show one here just to illustrate what they might look like. The scale here is in meters, so you get a sense of the scale of the device. It's usually a large toroidal device with large-scale magnet systems and other high heat flux components, as shown in sort of the pinkish red that form the balance of the power plant. If you're curious, you can look up this paper by Professor Najma Badi and read more about those concepts. So closing comments, we expect world energy demand to increase by 200% to 300% by mid-century. We also need to reduce CO2 emissions to about 1/5 of their 1990 levels at the same time. Those 2 points together imply that there is an extraordinary need for carbon-free energy sources. I would argue nuclear energy is one such source. It is certainly not the only source, but it is developed, it's scalable, and it's quantitatively safer than many competing sources, particularly fossil fuels. There are also emerging innovations like fourth-generation fission and fusion that might offer significant improvements over existing nuclear technologies today, but those require additional development, testing, and then deployment if it makes economic sense. Thank you.
Thanks for the talk about, sort of nuclear power, sort of past, present, and future. A couple of questions for you, though. You mentioned Generation 3 fission reactors with improved safety. Why are we not using those now, and what will it take to sort of get those online?
Well, we're beginning to build them around the world now. There's several under construction in China and in Europe. But most of the reactor fleet that's in operation today was built over the last several decades, and these systems have lifetimes of typically 40 to 60 years.
Okay.
And so the turnover timescale is just slow. So I would say we're going to have them in the future, but they were developed and licensed over the last 10 to 15 years.
Okay, so the design is already up and ready
Yes.
to be built. It's just a matter of doing the construction and getting them online.
That's right.
Okay, all right, good. So you showed an interesting graph that cost increase as the amount of power from nuclear power plants has increased, at least here and in France. And my understanding was that costs are supposed to go down as scale goes up. So why there's not an economy of scale with nuclear power plant, at least in this country and France?
Well, certainly there's expected to be an economy of scale in even these kinds of systems, but the experience in the US and France was that as a larger number of plants were built, we began to impose additional regulatory requirements on the design and operation of those plants, sometimes retroactively. There are also delays in the construction phase of some of those plants, either due to legal or technical issues that increase the capital cost of the power plant. And so as a consequence, that is the sort of history that has been observed. And in my view, clearly such an economy of scale has to begin to apply if this technology is going to really make it in the marketplace.
Yeah.
Whether that happens or not remains to be seen, frankly.
Yeah.
I would also note that the construction costs for these types of systems in Asia is that they're experiencing with recent construction is lower than the costs in the West. So we'll see how that plays out over the next decade or so.
Okay, so that brings up an important question. It's that most of the energy demand that's growing is in the developing world, in Asia and Africa and other places like that. Are nuclear power plants a reasonable solution for these areas?
Well, certainly I'm not aware of any large plans to build nuclear power plants in Africa at this point in time. Most of the anticipated new construction is in
Asia.
China, India, and in other sort of rapidly developing economies. Whether it's an appropriate choice for them, they seem to have made, the policymakers in those regions seem to have made the choice to deploy nuclear at some reasonable scale to be 10 to 20% of their electricity demand over the next several decades. It's not going to be the majority, but it will be some significant component. So they themselves seem to have made the choice, and they think it's an appropriate choice for them.
Okay. And they're building those now?
Yes.
Okay. So one of the issues we have here in the States is for long-term storage of the spent fuel. And you mentioned that geological storage is probably the ultimate answer for that. I know that we actually have a site here in the United States, but that it's never been used. Is there a technical reason it hasn't been used, or do you know what the reasons are?
The reasons that you're referring to Yucca Mountain, which was a site in Nevada, which was supposed to be used for long-term storage of U.S. spent fuel. And in the early days of the Obama administration, they made the choice to terminate that plan. And as far as I know, the main choice for that was not due to technical reasons. There are the other issue with the way that in the U.S. that particular site choice was made was it was not made in what's called a consent basis. That is, that the community itself was consulted with the possible decision to site a storage plant there. And so as a consequence, opposition built up. We do have a waste repository in this country for long-term waste in New Mexico, and the community that hosts it is actually quite happy to have it. Okay. And in Scandinavia, they've recently announced long-term geological storage sites in Sweden and Finland. But those choices were made on a consent basis, and so the local region was consulted, a thorough open discussion occurred, and the choice was made. And so I would say that's the differences between our experience here and as other regions is due not so much to technical choices, but it's to the process and the politics of it.
Okay. But we have a site in New Mexico that is now...
It's used for handling waste from military programs, but not from the civilian power plants.
Okay. Okay. Good. Okay. So after Fukushima, I know that many countries have sort of rethought their fission reactors. How are these new Generation 3 reactors that you mentioned different from Fukushima and presumably safer? And if they had been deployed in Fukushima, would the consequences have been different?
The Generation 3 ideas that I discussed in my lecture incorporate the concept of passive safety. So that what that means is that you don't have to require the intervention of a human-driven process to prevent a serious accident. So for example, in a Gen 3 reactor, even if you lost the forced coolant through the reactor core, the core is shut down, the waste heat generation, that heat can be removed simply by natural convection processes that operate independent of a electrically powered pump.
Okay.
And if you adopt those kinds of design principles, then you can either buy much longer time to respond before you have a serious incident, or you can make it impossible for such a serious incident to occur. And so that's the philosophy behind these designs.
So had they been deployed in Fukushima, they would probably be in much better shape now than they are.
If those kinds of concepts had been at Fukushima, they would not have had a meltdown within 8 to 12 hours after the loss of power at the power plant. Eventually, if you don't do anything, still you'll have a serious problem.
Okay.
But you have days or weeks to respond instead of a few hours before you have a catastrophe on your hands.
Okay, got it. Thanks. So fusion is clearly the reaction that powers the vast majority of energy on Earth. It's just that fusion takes place on the sun many million miles away. And then we get that power is sunlight back to the Earth. So clearly that's the real power source on Earth. So I guess the question to you is, how soon will we have a working fusion reactor going someplace on Earth?
This is the proverbial question people ask me when they find out that I work in fusion. Usually when they find out that I don't do cold fusion. The answer is the industrialized countries of the world have partnered together to build a device in France. It's called ITER, I-T-E-R, and it is anticipated to be, it is a physics experiment. It's not going to be a commercial power reactor, but we expect it to generate about 10 times more heat out than the heating that we put into the system. Okay. And the essential goal is to demonstrate the scientific feasibility of fusion energy production. If that works, and it's scheduled to begin those experiments in the 2020s, so basically next decade.
Okay.
The system is under construction now. If that works, then we have to take that and turn it into a commercial system. And I know the Europeans, the Koreans, and the Chinese are at the very beginning design studies of what a follow-on system would look like, what a demonstration, or what we call a demo reactor would look like. And so those designs are predicated on success of this ITER experiment and would then go forward in the 2030s. So, and that would be essentially the first prototypical commercial system. Whether it's viable in the marketplace, frankly, depends upon what the costs are of other competing sources and how good of a job we do in the fusion community in developing a competitive product. And I think, frankly, the jury is out on that question. Okay. I'm pretty sure that the physics will work, that we can make fusion energy. Whether it can be cost competitive, it's got to be determined in the marketplace.
Okay, so 7 to 8 years before the European sort of test version is done, maybe another 10 years after that before we could have something commercial. So what is the research you're doing in fusion that you're looking ahead, and what are the big breakthroughs that have to be made to make both of those things possible?
I think in our research here at UC San Diego, not just my own work, but the work of many colleagues here on campus, is focused on nearly all aspects of the fusion energy problem. Some of us work on the sort of the hot fuel, trying to learn how to confine that at the right conditions, and do so in a stable and long-term steady-state manner. Some of us are working on trying to develop the materials that you would build the reactor out of that would surround this hot plasma, so that those materials would be cheap, safe, reliable, and last long enough time for commercial product. And then others here are looking at what we call the system integration issue. That is, how do you take all the known physics, all the known engineering issues, and put that together into a product? What's that product look like? How much does it cost? Can you build it? And is it safe? And so we're working on all those aspects here at UCSD.
All right, well, best of luck in that research and the future of energy.
Thank you.